Okay, welcome everyone to this week's CDAC webinar. I'm delighted to introduce today's speaker, our close colleague Shanti Deemyad from the University of Utah. As many of you know, Shanti is an experimental condensed matter physicist specializing in studies of quantum materials, pressure-induced transformations, and measurements of structural, electronic, and magnetic properties of materials with a focus on light elements in particular. Shanti obtained her bachelor's degree from Sharif University in Tehran, which has produced a number of excellent scientists. Then moved to Washington University in St. Louis, where she worked with Jim Schilling, former CDAC partner. Great that you're joining us, Jim. Shanti obtained her PhD in 2004 there, and then moved to Harvard to work with Ike Silveira in 2010. She moved to Utah as an assistant professor and is now an associate professor in the Department of Physics. Shanti is also very active in the high pressure community, for example, having been chair and co-chair of the High Pressure Gordon Conference in 2016 and 14. And she's the current treasurer and an executive committee member of ARAP, the International High Pressure Society. Shanti is also very active as a user in high pressure DOE and NSF facilities, including the APS, SNS, and the MagLab. And she's also been a longtime collaborator in CDAC. So welcome, Shanti. We're looking forward to your talk.
Thank you so much, Russ, for the invitation and for a very generous introduction. I'm glad to be here. We are nearing a year from the time that COVID started. I mean, lockdown sort of started around the world. And today I'm going to talk about symmetry breaking and quantum effects in phase transitions. But where I am, I'm at University of Utah. This is where Utah is, for those of you who've never been here. So it's a okay place to be. Most of these places are 1 or 2 hours maximum away from where I'm sitting. And it's a good place to be during the time that you're locked down. You can get out and get some fresh air. This is my lab at the University of Utah, which has been sadly very empty these days. We are only allowed to take turns to be present and do experiments there, and it's occupied by a bunch of regular condensed matter instruments. But most importantly, this is the people that have worked in my group, the pictures of them. And there are many more. I couldn't fit in there, all of them. And in the red rectangle, you can see the number of students and postdocs: Dr. Weijia Kai, Tessa McNamee, Mahindra Dunawal, Dr. Mahindra Dunawal, Dr. Rong Zhang, Tushar Bomik, and Tomal Hossain, that have been closely worked in the recent projects of the group. And we also had a large number of collaborators, and we have been generously offered beam times from CDAC, and we're grateful to Ravi and Russ to allow us during this lockdown time to remain productive. And our research has been funded by National Science Foundation and Department of Energy. Okay. So my group basically is interested in material properties, and it always been to justify that what is exciting about this is that it always been about the material properties that allowed us to move our technology forward, and that is going back from the Stone Age to Bronze Age and Iron Age, all the way to the time that we started understanding more exotic states of matter like semiconductors, ferromagnetism, superconductivity, materials that have different densities, light, ultralight materials that allowed us to move our technology away. So, however, each state of matter, as we know, is only limited to a certain boundaries in the phase space, in the temperature and pressure. And as we change the conditions around the material, the state of matter can change. And particularly, what drives our research is that what drives phase transition, something that excites us very much is that what drives phase transition. And simple answer is that you basically change a parameter and you're going from one state of matter to another state of matter. These can be temperature, pressure, chemical composition, magnetic field, or electric field. And In my group, we are using the variations of these parameters to study materials. And also we are trying to understand that what causes, what is the microscopic interactions and conditions that causes the material properties. I'm going to show you a range of different projects that we have done in the group. I'm not going to talk about any particular one of them. I'm happy to discuss them afterwards, but I just want to show you what kind of stuff we are doing. And here are like a few examples of the things that we have been looking at. For example, we are using ultra-fast spectroscopy to look at the dynamics of the electron and lattice interactions in materials. And this is a work that we have done with collaborators at University of Utah and National Renewable Energy Laboratory. In other experiments, we use spectroscopic methods like Raman spectroscopy and X-ray to look at the amorphization of the materials, which is very common in hydrocarbons. Another example would be the pressure induced superconductivity. Here we work with chemistry groups at Northwestern University, and we also work in for structural studies. We work with the HPCAT and CDAC and JC Cars. And here we are looking at compounds that are closely related to, for example, some of the high TC materials on conventional superconductors. And we are looking at their superconductivity produced under pressure. So pressure is a major knob, obviously, that we are using in our group. Some of the other things, I'm just going to go through these other three, is that this work is like basically competitive ground states. We are looking at the competitive ground, electronic ground state, like charge density wave and superconductivity. That is very important, basically, actually, state of both of them are pretty interesting state of matter, that they are competitive phases in most it can be competitive, we don't know exactly the theory, but they can be connected to each other. So, and this is a material that we found that we were studying the correlation between its CDW and superconductivity under pressure. Other things is that new electronic state of matter, like ferroelectricity. And sometimes the nature goes the opposite way that one would assume that it should do, and thus counterintuitive things, like, and this is a pressure-induced ferroelectricity, recent work that just got accepted and a couple of weeks ago. Other things is that, and in these materials, we also use, for studying these materials, we are heavily dependent on the structural studies that are done through experiments that we are doing in APS. Other group of experiments that we have done is that magnetism under pressure. And here we are working with group at UC Davis, where we are using NV Center to look at the local magnetism in materials, together with the techniques that I learned from when I was a student with Jim and doing AC magnetic susceptibility. And as you can see throughout all these studies, we are heavily collaborating with the theory groups, and structures and theory are the two components of the research that is important for us. In this talk, I'm not going to go through these states of matter, but regardless, the idea of phase transition and how we can look at the interactions inside of the material at extreme conditions drives the motivation of our research. So the outline of what I'm going to talk for the rest of the time is that I want to talk about generally about the structural phase transition under pressure. I'm going to specifically talk about two different types of dynamic disorders in crystals and quantum phase transitions, and at the same time, the symmetry breaking and electronic effects, and highlight the studies that we have done on lithium throughout the years and more recent works that we have done. Okay, so structures at high pressure. So when you are trying to pack things very efficiently, you put them in some kind of order. Often putting order helps. And when you are looking at going across the axis of pressure, pressure also allows you to pack things pretty well. So in some sense, you can think there is a relation between order, pressure, and packing. And for example, if you look at something like a temperature axis, when you are increasing the temperature of a material, you often go to disordered phase, because and this is what happens often. But what goes under pressure is that as you pressurize the material across an isotherm, often you are going to a more ordered phase. That is what you would expect. So this is sort of a general idea that we think that the universal melting curve should look like this. So basically liquid is disordered, solid is ordered, and to increase the, as you are going to increase the pressure, this melting line is going to increase. Now, there are two types of dynamic disorders that we have in materials. There are phonons that basically are temperature dependent, that are amplitude is temperature dependent, and then there is zero-point motion. And this basically zero-point motion is something that we are very interested about, and I'm going to talk about it more today. And these are basically types of quantum mechanical effects that exist at zero temperature, which means that if you even remove totally the axis of temperature and stay at zero temperature, you still can get the phase transitions by changing other parameters like magnetic field, electric field, or pressure. And pressure turns out to be an extremely important and powerful tool to study these quantum phase transitions, and that interest a lot of modern research. So what do we mean by these disorder things is that if you think about the classical solid, you think, and these are like the model of these nuclei that are sitting on the two-dimensional lattice of some kind of a two-dimensional rectangular lattice, and you can see the classical solid is the one that basically this delocalization of the wave function is very small compared to the interatomic distances, or you can say the Broglie wavelength is much, much smaller than the interatomic distance. And for example, if you are going to increase the amplitude of vibrations in this type of solid, you are going to get melting. So you are going, at some point when the amplitude of this vibration becomes close to interatomic distances, like it becomes 10% of that, Lindemann criteria of melting is a very naive sort of model. It's going to cause this classical solids to melt. And this is something that most of the solids that we know of, they fall into this category. You can assume nuclei is classical, the Broglie wavelength, the quantum effects are gone, and everything is dominated basically by the amplitude of the vibrations is dominated by temperature. Now, let's look at the other case of what do we mean by quantum solids. The quantum solids obviously is solid that the Broglie wavelength gets close to this interatomic distances, and basically the translational symmetry is going to break to basically to avoid the overlap of these hard cores, and you're having this and there's a similarity here. Here's the amplitude of the thermal vibration getting close to interatomic distances. You are going to get instability in the lattice or melting. Here, similarly, if you get this delocalization or basically quantum zero motion disorder is sufficient compared to the interatomic distances, you're going to get the same effect, but it's not the thermodynamic melting, it's a quantum melting. And it's basically coming from uncertainty principle. Now, sometimes the examples of quantum solids at ambient pressure are hydrogen and helium. We know that, for example, helium never freezes down to zero temperature. So now some years ago, de Boer defined this parameter called de Boer parameter, which is simply the ratio of this de Broglie wavelength by R, and said, this is the measure of quantumness of a material. So basically, when the material becomes, this de Boer parameter becomes large, or the Broglie wavelength becomes comparable to interatomic distances, then we get quantum effects. I mean, quantumness effects become important, or this quantum disorder becomes important in the phase transitions. And as you can see, this this de Boer parameter is proportional of a few things. H is the Planck constant, which is not going to change. But things that can change is the R, which is interatomic type of distance, or the sort of the potential width, and the mass, and also the type of the interactions that we have. Obviously, the type of interactions are also always proportional to this distances. And now, for every high pressure person who's sitting here, immediately we can see that this quantumness can be easily, because both R and E are dependent on the distance or density, pressure is a wonderful tool to adjust this de Boer parameter. And it turns out if you use this basically uncertainty principle and play around a tiny bit, we can see that this de Boer parameter in materials is going to be proportional to R over N over 2 minus 1, which is N is like a type of interaction. If you have very short range interaction, we have 1 over R to the, I don't know, 12. If you have very long range interactions, we have this N is a small. And and obviously for large de Boer parameter, we are looking for lighter stuff. So because this is 1 over square root of mass. Now, if you look at this equation closely, you can see that this N over 2 minus 1 is, if it's less than 1, this exponent is negative. And as we increase the pressure, the R is going down and the Boer parameter in that case goes up. So that is the case for N is less than 2, or we have long range interaction, something like Coulomb type interaction where N is roughly 1. And but if you have something like short range interactions like van der Waals materials where N is very large, then this exponent is positive. And as you increase the pressure, the R is going to go, basically R is going to go down, and you are going to have basically the Boer parameter is going to diminish. So high pressure can be increasing quantumness in specific cases where the potential behaves certain way. Now, based on that, some years ago, it has been proposed that you can have these two classes of melting, like basically based on order-disorder behavior. One is universal one, which is for most of the things that as you increase the pressure, this is the pressure axis, as you pressure the thing, the disorder becomes less and less favorable, and material stays in the crystalline phase more and more. And the other, due to the thermal effects, but then this other one is true for the materials that are highly quantum. And in this case, that as you increase the pressure is not only basically the packing that is important, but also disorder that coming from the 0 point effects that becomes relevant, and you can get quantum melting at some point. So this 0 point effect, if it increases enhanced by pressure, you get the quantum melting. And this is something that people have been looking, and then basically one of the interesting consequences is that can we get quantum melting in a material? Can we get examples, something like helium 3 and 4, but at high pressures in materials, and what kind of physical properties that state of matter is going to have? So basically, based on the definition of the Boer parameter, we're looking for low mass stuff that material that are having these long range interactions, and they maintain them in high range of pressures. And obviously the best case would be hydrogen, because hydrogen supposedly becomes metallic, is extremely light. And well, helium is not very helpful because it's true that it's quantum solid at ambient pressure, but it remains non-metallic as far as we know. Hydrogen, on the other hand, becomes metallic, but the pressures are extremely large. It's 0.5 terapascal. And how do we want to really look at the material properties is a challenge that high pressure community has to address before we get to hydrogen as a material to study for these quantum effects. On the other hand, if we go to the third lightest element, which is lithium, this is already a metal. And it can give us, and it's super light. I mean, if you compare, for example, the lithium-6, which is one of the stable isotopes of lithium, you can see that it's not that much heavier than helium-4, which is a known quantum solid. And basically, the idea is that the interactions are different. I'm oversimplifying everything, but lithium is a good case for looking at this. And it's also a very simple system at ambient condition. You can approximate it with the empty lattice models. It has a pretty well spherical Fermi surface. It has a very simple structure. It has two isotopes that are known, stable isotopes, lithium-6 and 7. Atomic physicists love these isotopes because one of them is fermionic, one of them is bosonic, so they can even study the statistics. And then one would say, okay, let's get this lithium, squeeze it, and get this quantum liquid ground state. But the problem is that obviously it's not as simple as it is. Everything that I said was based on the fact that, okay, we only have solid versus liquid, and there's no other ways that the lattice can find an easier way to basically lower its energy. So we go from order to disorder and done. That's it. In fact, this is true only in the absence of pressure-induced symmetry-breaking structural phase transitions that we get, that basically this kind of peak in the melting line is coming from, can be assumed that is coming from the quantum effect. And the electronic effects and symmetry breaking in condensed matter is something that all of us know, and we have seen it from very early on in condensed matter physics, that, for example, we have parallel distortions, that if you have a one-dimensional lattice of ions, and you are going to assume that if you put them separate from by equal distances, that's going to be a good way to arrange these. But then the electronic basically distortion, the effects cause this lattice to actually form this bound state. I mean, this basically dimerization, and a gap is going to open, energy gap is going to open up. So this is a model that we all learned in the condensed matter physics class. First thing. But then also there are other things like charge density wave in higher dimensions, is the two-dimensional effect that is basically a static modulations of the lattice. Sometimes it's related to this exact parallel distortion. The origin of it is that. Sometimes there are other things like the simple energy lowering or shear can cause this CDW, charge density waves, that are very important topic actually in condensed matter, in two-dimensional things. And you also have Jan-Teller, for example, distortion. If you have it in 3D, you have a molecule that is not linear, and then basically it's going to distort, to get distorted to remove the degeneracy of the energy state. So these are the things that we know, that the lattice is not going to remain all the way ordered till the liquid phase is going to come up. Before that, we are going to have all these effects that are going to distort the lattice. In fact, from the simplest of elements that are alkali metals, they basically, we start seeing these effects. For example, both sodium and potassium, they're known to have charge density wave have shown, and this has been for a while, and they're more recent. These are the first studies, but they're more recent studies that they have confirmed this possible presence of this charge density wave in alkalis. This is as function of temperature. You cool them down and they do this charge density wave. Now, as function of pressure, things are even more drastic. You stay at constant temperature and you pressurize these. All of them, they go through this sequence of phase transition. Initially, they go to more packing, but eventually the electronic effects become so dominant that they go to this actually exceedingly low symmetry phases that are very, very counterintuitive. And as a consequence of that, for example, if you want to see quantum melting or maximum in melting block as signature of quantum melting, good luck, because this is the melting temperature of all of these things. And because they go to the lower symmetry phases, they get their maximum. That is not necessarily, and I can say that not probably very much in case of something like cesium that is very heavy, originated in the quantum effects. So, and this is true for the melting curve of lithium. And this is like this is a work that has been done in APS by Frost et al. A couple of years ago. But the squares are the studies that we have done a few years ago. On the melting line of the lithium. Yes, it has a melting line that has a maximum, and it's pretty low temperature. It goes to room temperature at 500,000 atmosphere, but also it's going through all these structural symmetry breaking, structural phase transition. So we cannot say the lowering of melting is initiated because of the quantum effects, but it could be originating from that, the difference in the energetic of these low symmetry phases and the liquid. So the melting is more, goes to melting temperature goes down. Okay, so this is a very pretty entangled place. Everything is entangled, the electronic effect, the lattice effect, everything is getting together. And my group has been working very hard to basically to open up this very complicated situation and try to basically, to the best of our knowledge, to basically take things apart. And here it is, going back to our de Boer parameter. If you're looking at this quantumness, we are really looking for the mass effect. And one thing that I learned from very early on is that keep everything constant and change one thing so you know what is the effect. So we try to keep as much as possible everything constant, but just changing the mass. And for that, we can rely on isotopes. And this is where these very low Z and light elements are wonderful, because the differences between their isotopic masses is huge, like 15% in case of lithium. 6 and 7. So so we can rely on that, because the isotope of the same material should not have very different physical properties. And if we see these huge differences, then we know it's originating from the quantum effect. So that's where I'm going with this from now on. And basically another thing is that we are going to look is that we are going to go to low temperature to minimize the effects of disorders coming from the non-quantum contributions, like from the phonons. Now, I'm not by any means the first one who has thought about this, and these studies have been there for a very, very long time, and people have looked at the isotope effects in lithium. And this is a work that we have done, and we looked at one of the things that we looked at is the superconductivity. And I tell you where I got very excited about superconductivity. This is coming from 2003 when I was working with Jim, and I came up, we measured the superconducting transition of lithium. We were one of the 3 groups that we measured the superconductivity of lithium under pressure. And this is a curve that came up with, and that is from lithium, natural lithium, that is mostly lithium 7. Now, if we think about this as a simple metal, a BCS type of metal, then for lithium 6, we should, for example, see this is the dotted line is going to be where we are going to see this isotope effect. And that's what we looked at. And we did obviously very careful measurement, because you can't just basically take 2 isotopes, make 2 measurements and make a comparison. You have to study these side by sides, because number one, the differences are very small. So you have to be able to compare 1 Kelvin in a large size of the diamond cell for the samples that are tiny, tiny. And we all know that is very difficult. And secondly, the kinetic effects. The thermal paths can be very, very different for between different experiments, and we land in different parts of the phase space that can basically make our experiments invalid. And what we have done invalid, and what we've done is that we measured the samples in the same diamond cell next to each other. And what we've seen was quite remarkable. We saw a difference. The red is lithium 6, and the black is lithium 7. So now what one would expect is that this was what we were basically we were thinking about lithium 6 should do if you're having a normal isotope effect. And instead it did this kind of thing. And the question was what is going on? So soon after these measurements, we looked at the structural phase boundaries of lithium, and we saw, oh wow, okay, there is a lot of boundaries. I mean, the structural boundaries of lithium is very complex, and is right here, right around 20 GPa. There are lots of different structures. Could it be that these different structures, they have different boundaries? Because it's unlikely that something like lithium shows non-BCS type of superconductivity. One cannot for sure exclude. It's just unlikely. So, and it came out that the theoretical paper that came out soon after showed that actually right around 20 GPa, between the structural phase boundaries of lithium, the energetics are tiny bit, so very small differences. And that made us think that, okay, if we have these ups and downs, maybe this is what we see in lithium 7 in large pressure range. Maybe that's how explains this ups and downs that we see in lithium 6 by the displacement of the phase boundaries. So that is what we went after next. And the particular thing was that this area of this low symmetry phase that was thought to be close to the superconductivity, we wanted to study these and see how the superconductivity can be related with this phase boundary. This is a Martensitic phase transition, and these boundaries were never been really studied. And basically, when you cool down the lithium from BCC, even at the ambient pressure, goes to this stacking fault Martensitic phase. And the interesting thing about it is that this phase is actually theoretically is not predicted to be energetically favorable. Theories are suggesting, even the best theories are suggesting, that when you cool down from BCC, you first have to land in FCC, and that is not the case. We always end up in this Martensite phase. And this is an early study that was showing that even though that during cooling we were going from BCC to this Martensite, when we warm up, we are going to recover some of the FCC. And that was a smoking gun that was telling people that maybe this FCC in fact is a stable phase. Is just this Martensitic, for some other reasons, is happening. There is a kinetic effects involved. And we looked at this, So we looked at this region. We wanted to find these boundaries because they weren't studied, and we wanted to also understand the isotope effect in them because that's what we were thinking originating these problems. So we did some, I'm going to walk quickly through these. This is neutron studies in Paris Edinburgh cell that we have done in Oak Ridge National Lab. And here you can see that as I'm cooling down the lithium at 2 GPa, it's going to start having these extra peaks that overlap with this 9R or Martensite. So we enter the 9R phase. Now, as I warm it up, on the other hand, from 9R, I'm going to start see mixture of FCC and BCC, and 9R goes away. And I want to compare it with these early studies from 1990 that they see the same thing. You go from BCC to 9R, but when you warm up, you recover some BCC from FCC. So we saw the same thing at high pressure. Now, this was one path. Now, the next path we did at higher pressure. So we went basically 5 GPa. And what we saw is that we go straight from BCC to FCC, and no indication whatsoever of 9R has been observed. And the same thing was confirmed in the experiments that we later did in HPCAT that basically showed us that when we are cooling down from FCC, if we enter BCC, if we enter FCC, we stay in FCC. And we basically completed this work by doing these measurements that lithium 6, this is like lithium 7, that is basically, this is the red squares are showing BCC, green are showing FCC, and blue is showing mixed phase, this Martensite. And we saw that basically these boundaries, hypothetical boundaries, actually are not valid. And this is where we're going to end up. We cool down from BCC, we end up in this 9R structure. And the question that was staying was that, okay, let's look at the isotope effect. Is that showing the same thing? And I don't want to make it short story. We did again side-by-side measurements, and we saw, wow, okay, lithium 6 and 7, they have different boundaries. They actually, the boundaries of this blue region, which is Martensite, differs from each other, shifts from each other. And it solidifies the idea that nothing else that we know other than helium, isotopes of helium, show differences in boundaries of their solid phases, as far as we know. This is a very old study, so it has to be revisited, in my view. The question is that we think that the basically differences in these boundaries of lithium 6 and 7 is related to the presence of some kind of dynamic effects coming from disorders that are originated in the 0 point motion. Now, the last one more question was that, is this Martensitic the ground state of lithium? Well, we know that every time we cool down, the lithium lands in this 9R, and that was a great argument that this is the ground state. Okay, we did two things. The second thing, I'm going to hold it for the next part. That is, we looked at the basically electronic structure of the lithium, and but we keep it for later. But for the one thing we did is that, okay, what if instead of, we know that if we go down in the cool down, we always land from FCC, BCC to 9R. We also, if we pressurized, we go from 9R to FCC. So that was basically, that was the path everybody took, and everybody thought that is basically confirmed that this is the ground state experimentally. What if we, theoretically, FCC was the ground state? What if instead of doing cooling down, we just go around? First, make sure that lithium goes from BCC to FCC, and this is high temperature effect. And then we cool down, so still you're in FCC, and then we back off and see if if 9R is the ground state, supposedly going back and forth, we should recover some of it. And this is what we did, and here is what we saw. This is like red is BCC, green is FCC, and blue as 9R. And we see for both lithium 6 and 7, if we warmed up, we basically pressurized, we go from BCC to FCC, back and forth, we can go between the two phases, cool down, stay in FCC, back off, and even warm up, and we never recovered 9R. So we basically synthesized, even at 0 pressure, this FCC, or the ground state of what we believe is the ground state of lithium. The physics of it is that, well, as you look at GPS, is not always the shortest route that is basically the ground state or lowest energy state where you save maximum amount of gas that is going to get you to the destination fastest. And this is what we have to be very careful every time we do these high pressure experiments, that the fastest route is not necessarily the ground state. And a lot of times these kinetic effects are taking over to take you to a different metastable phases. And this is a cartoon that we made that is basically, even though Martensitic is not the ground state, but is faster. At a lower pressure, we go there. But if we are already finding another path that take us to the ground state or lower energy state, we are going to stay there. Okay, so we probed the kinetic effects. That is basically through this synthesis of the ground state through alternative path. And then we also saw the signature of dynamic instabilities due to the presence of the 0 point effect. And through the isotope studies and through the superconductivity studies. But the next and more important question was that lithium, which has this very sophisticated electronic structure, how does this electronic instabilities contribute to the phase transition of lithium? And that was a very the question that we spent the past few years, extensively studying. And the question first, I encountered this question. It existed probably before, but by the seminal paper by Neutron and Ashcroft, that in 1909 they predict that the presence of these combination of parallel type instabilities and the Ion-Teller distortions in compressed lithium would drive it into a phase that it may actually, the electron actually form this, the lithium actually itself may start pairing, and other more exotic state of matter, they have been predicted subsequently after that. And it was predicted that lithium becomes a semiconductor. And this indeed was confirmed later on by a group of Takahiro Matsuka and Katsuya Shimizu, where they see that the resistance of lithium changes over several orders of magnitude as you pressurize it, and it becomes a semiconductor. Now, more recent experiments that have been, theories have been come with even more exotic electronic effects in lithium. And these are two studies, one by Jeffrey Newton's group and one by Rolf Hoffman and Stanimir Bonev, Jifeng, and Neil Ashcroft. I named everybody, so I meant so everyone, that they basically is topological states that exist in lithium that can be created under pressure. So this material at different pressure, it may actually show that it has, this is a topological semi-metal or Dirac semi-metal. And it's very exciting states of matter to understand. So as for an experimentalist, we really want, one of the good ways to look at the electronic properties of a metal is look at its Fermi surface. So for example, if you look at the Fermi surface of lithium, and this is a work that we've done in collaboration also with, this is a work that the theory part of it is done by Sabli Alatrish, Stanimir Bonev, Rolf Hoffman, and Neil Ashcroft. And basically, you can see that they calculate the Fermi surface of lithium, and you can see that, for example, BCC, which is purely spherical, if it turns into FCC, start having these necks. And if you go to this Martensitic phase, it has this completely different structure, Fermi surface. The problem is that these studies are so difficult on lithium. Lithium is very soft, it distorts very much, and then the presence of this Martensitic transition makes the fermiology experiments extremely difficult. So the latest experiments have been go back to late 1990s, so we needed to revisit these experiments, and that's what we did in the experimental side of the things. And this is the fermiology. This is basically this peak that you're seeing is telling us that this spherical part of the Fermi surface, the location of this spherical part of the Fermi surface, and you see it's split, it's anisotropic. So we see that by experiments that we have done in high magnetic field lab, that there is a splitting. So the question was, we compare it to the theory, and here we are collaborating very closely with theory, and we see, okay, we see some kind of a splitting in FCC. 9R distinctly doesn't have anything in this area, this martensite, and that was another indication that this 9R not only is not the ground state, but probably is not 9R altogether. So, but instead, these two peaks, the presence of these two peaks gave us an idea that maybe we are looking at something that is combination of two other structures, BCC plus something else, and maybe something close to FCC. And well, you have to calibrate yourself. You have to make sure that you're not really doing an experiment and you see this splitting because of some kind of an isotropy that exists in your calibration of your magnetic field or so. So we looked at something simpler, something that is even more spherical, and that is sodium. And here is sodium. It's stunningly, sharp peak. It doesn't show any splitting. So next thing that we have done is that, okay, we moved this experiment. We were confident that, okay, we are seeing this splitting, and we have done lithium and sodium side by side. We did lots of measurements, and these two A and B is basically, as we are changing the orientation of the sample, we are adding up all these peaks, and this is what we get. Lithium has this broad peak. This is the same frequency interval, and the range is the same. Values are different, but the range is the same. Sodium is sharp peak, whereas lithium is very broad and distorted. Now, if you look at this lithium peak to what theoretically we calculate for the FCC versus BCC, it looks like two sets of peaks exist, and this is one goes back to BCC and one goes to FCC. So that is the first measurement that we could really find resolve these peaks, and we are very excited about it. This is unpublished work that we're working on now. Now we have to do pressure. So we have to really see that the motivation is to go to really high pressure. And this is a mini MEDAC that Stan Tozer had made that can take you to really high magnetic fields. And this is a picture of a lithium that is wrapped inside of this coil. You can see that in the transmitted light, and that basically, we are measuring Shubnikov-de-Haas or resistance of the sample, but without touching it. This is an indirect measurement that you're using the tunnel diode oscillator. Very, very interesting experiments. So nothing about this experiments were easy. This was like, it took a village basically to do this, including bringing a theorist to MagLab, that Sabri Alatra. She came with us, and this was the first time he was touching the dill fridge and bringing down the probes. Here is a team in MagLab, Stan Tozer, Audrey Gorkoviak, and William Konitlo, that they did the TDO design. And here's the look of my excited graduate student, Tushar Domikat. I think it was at 3 a.m. and I wasn't actually there, that when he detects first the quantum oscillations in lithium at high pressure. And that was really, really exciting. And what we see here is that basically, as you are increasing the pressure to what most of us think that is very low pressure, we see this nice shift in the location of the peak. And as we are comparing this, these are these green, dark green data is the experimental data, and the light green and red are the theoretical data for theory for BCC and predicted theory for FCC. And what we see is our data is very much close to location of this peak, as change shift with the peak is very close to what FCC should be. So we think the structure, the ground state of the structure of lithium that is very low temperatures, the 300 milli-K, it's closely related to FCC structure based on this observation. Now, the next question, and it's more than just a fact of the exact value, because that's less relevant, but how the trend changes BCC versus FCC, that makes us think that this is more closely related to FCC. Now, the next thing in every good fermiology experiment is like how electrons, they interact with the lattice, or measuring the electron effective mass. And the way you do this is that you increase the temperature. And as you increase the temperature, you see how these oscillations, quantum oscillations, die off. And this is what we have done at 1.7 GPa in lithium. And we see that the effective mass of electron is 2.3. The effective mass of electron at ambient pressure is, for lithium, is 2.1. So there is a slight increase. And when we compare this with, for example, sodium, we see that sodium, the effective mass of electron decreases, which means that it becomes more of an ideal metal. Whereas in lithium, it becomes less of a free electron system. So we are really looking into this problem. How can we explain? Actually, lithium does what we are supposedly do, because as you are going to higher pressures, you assume that the lattice becomes more interacting with where the lattice starts interacting more efficiently with the electrons, and therefore the electrons become less free electron-like. But in case of sodium, there is this opposite effect. And similarly, in potassium, this has been observed. So one way that we can think about is that if sodium also has a martensitic transition, but in contrast to lithium, that is martensitic transition enhances under pressure. In sodium, this goes down. It dies off under pressure. And what we are thinking is that it could be that the presence of this disordered phase is going to basically lead lithium to show less of a free electron behavior as we go to higher pressure. So this is now basically, there are many more open questions. We are basically pushing forward to get more out of lithium. We need to look at the, well, okay, do we see, I mean, we don't think this, and other alkalis, that what is the origin of CDW? Is it like CDW really in competition, other alkalis like sodium and potassium, that superconductivity have not been observed in them, or is preventing them? Is martensitic transition is a competitive phase with superconductivity? Are there topological phases through these measurements? Are there dimerization electrides? And we are going to be closely looking at instability and competitive phases, and this is the work to be continued. As of now, we established the effect of dynamic disorder through zero-point effect in the structural phase boundaries of lithium, and we showed that lithium remains a nearly free electron system, not as much as sodium, but in moderate pressures. And we established methodologies and that we can use to extend the range that we are looking at this Fermi surface of these alkalis to higher pressures. Now, the remaining questions would be, do lattice or dynamics or electronic instabilities of lithium lead to symmetry breaking structural phase transitions, or do lithium form electride at extreme conditions? Does it have topological states? And many more questions that are left. It's a great system to study condensed matter. Everything is complex. Maybe lithium gives us a way to look at things. It's a complete system that has quantum effect, normal vibrational effects, and it's a whole package, full package that gives us a lot of opportunities to look at many different materials in relatively simple system. And this is my group, the pictures of my group. The very recent picture of my student, Maura Hicks, that she basically moved the lab to her home with a bunch of lenses. That was to continue the research at home, learning optics on her desk. So I want to highlight that. And I'm grateful to all of you for listening to me. Thank you.
Thank you. Yeah, it's a terrific talk. Beautiful slides. And the measurements of the Fermi surfaces, really very impressive. So questions, comments for Shanti? Just speak up or put your questions or comments in the chat box.
Hi, Shanti, it's Eva.
Hey, Eva.
Great talk. I was wondering, has anyone looked, I mean, what you talked about reminded me of kinetic versus thermodynamic control in chemical reactions, which is what chemists think about all the time. Has anyone looked at the transformation pathways between the different phases of lithium? I'm guessing it would be quite difficult to do it computationally, but it might be quite interesting.
I don't think anybody has done the different pathways computationally. And that's a very interesting, actually, question. We have done that one study that we went just BCC, FCC, and the Martensitic. To my knowledge, no one has done any other pathways to see if you can go between these phases. And I believe that, I mean, not I believe, but I guess, my guess is that there is, if you look at something that has basically, let's see if I can something that has such a complicated structural phase boundaries, I believe that there are going to be more than just this one place that we are going to see the instability, and there are going to be many of these phases can be metastable actually, because most of them, they have been created by isotherm. So you just basically, no, I'm sorry, isobars. So basically you kept, isotherm. You kept the temperature the same and you pressed through. So, and there is where you get a lot of instabilities, lots of metastabilities. That's a recipe for creating metastability, to stay on an isotherm and press.
Yeah, that would be, that's very interesting. It would be cool if someone could look for the transition states, even though that would be very difficult, I think. Thanks.
Yeah, thank you. Yeah, that was a great suggestion. Yes.
Thanks. More questions? Perhaps a technical one. Lithium is difficult to study, and I'm wondering if you would say a little bit more about techniques you use to keep it from reacting with the components of the diamond cell. Maybe staying at very low temperature certainly helps, but what else are you doing in the way of preparing the samples?
Yeah, that's actually very important and great question. So what we did is that we used the pressure medium, number one, for all of our studies pretty much. So we used helium as pressure medium. So in a picture that I showed here, I didn't go through the pictures because I thought it's going to be too dense. So you can see, for example, the lithium that is embedded inside of the helium as pressure medium. So that's one thing. The other thing that we have done is that we coated our diamonds, because lithium is pretty non-reactive to alumina, but alumina can scatter X-rays. So it's basically makes trouble for our X-ray studies. So what we did is that we had a very thin film of alumina that was sputter on top of the diamonds that would give only 15 nanometers or so, enough to protect chemically the lithium from touching the diamond, but at the same time to keep it non-reactive. But the pressure medium, I think it's very, very efficient tool as well. We have done measurements with and without pressure medium. In both cases, we did use the coating. I think the experiments that I've done in Jim's lab for the superconductivity, it's very interesting thing is that the points that you're seeing here, the black points were taken when we pressurized, and the open circles are where we depressurize. So we could go to, actually we went higher. We went to higher pressures, but we obviously, for reasons at the time we didn't know, the superconductivity suddenly goes away, but because it becomes a semiconductor. And but then we can see that these open circles, and we could even recover. So we didn't even break the diamonds. So that was like a, you can work with lithium if you keep the temperature low, if you protect the diamonds, and you use. One interesting work that I really hope to on my wish list is to look at the electron lattice interaction through ultrafast experiments, to look at that, how these change under pressure, and that's quite doable, because this optical probe is much easier than touching the sample that can cause chemical reactions. So,
yeah, thanks. Very helpful. More questions?
Just a comment. If you look at the periodic table of superconductivity, of course, hydrogen will be a room temperature superconductor. That's obvious, but lithium becomes superconducting, and so does rubidium and cesium. But the elements in between, the alkalis, sodium and potassium, haven't. Wouldn't that be something interesting to look at?
So that's one of the things that I brought up. That is that sodium and potassium, they have charge density weight. So it could be that at high pressure, we destroy that charge density. But ambient pressure, I don't think the reason they are not superconducting is because of this charge density weight. At higher pressure, they may become superconductor. The thing about sodium is that it remains awfully free electron-like to 1 megabar. So if anything happens, I would guess that is about 1 megabar. So, and actually our theory collaborations with actually Rolf and Neil and Stanimir and Sabri showed that actually sodium they have done these calculations, and sodium remains completely spherical Fermi surface all the way to megabar. So I doubt that in BCC it would superconduct. But potassium is a different story, of course. So that's an interesting. And Jim, this is also, I have to give credit that this is a very recent discovery. Came from the last thing that you did in WashU, right? The rubidium study.
Yeah, that was, yeah, Yuhang Deng did it. I just watched.
Yeah, okay.
So I don't remember which alkali, but I think it's potassium and one more. Picard has a paper predicting that it becomes some exotic magnetic state under pressure.
Okay.
Right, that hasn't been found yet.
So yeah, we are in this basically, I heard this thing that is like a border of disorder as Wild West of superconductivity at some APS. I don't know who said that, but something in that those lines. So there is so many things going on inside of these things. Sometimes, I mean, a lot of them, they can be having a superconducting ground state in certain parts of phase diagram, but they also may have like magnetic ground state or other kinds of ground state, like charge density wave or other kinds of ground states. So one has to really look, and theory is really essential in seeing what is going to be. But one thing that we neither theory or experiment is very efficient is detecting this quantum effects, and isotope effects gives us some tools, not everything, because still we are dominated by these kinetic barriers that can mess up with everything. We don't do this carefully, we can end up having whatever we want without. Yep.
Can I ask you a question?
Sure.
I'm Hyun Park from UIC. So you mentioned that so you can identify the disordered structure phases using the quantum oscillation measurement, right? From the multiple peaks, right?
We can look at the, I mean, we can basically, what we can say is that how does the Fermi surface look like? And then we do, I mean, we are working closely with theoretical groups that for different structures, they calculate the Fermi surface. And we compare our quantum oscillation measurements. I'm going to try to get you there. So for example, this is a example. So this is the spherical part of the Fermi surface of lithium, and with quantum oscillations, and this is different structures, how they should look like.
Right.
And by comparing these with these models, we can get an idea if the structures that we think for some of these elements or materials that they're in place, are they consistent or not? So that's one of the things that we get inspiration. But really the main reason that we're looking at these is beyond that, is way beyond that. We really want to understand how does the Fermi surface of these metals look like and how they change with pressure. Nesting, Fermi surface nesting is one of the ways that is thought that these metals, they become superconductor. Lithium becomes superconductors. That I think Warren Pickett had a paper on that. And it's very nice to see if we see this kind of Fermi surface nesting where the superconductivity starts.
So can you tell also what's the nature of this disorder? Like is it random disorder or the phase separation or?
You mean the Martensitic? Okay, so that is a shear-driven transition from are you referring to 9R transition, the Martensitic transition, which is a disordered?
Any disorder you have like structurally have a competition between. I mean, you have a very small energy difference between different structures, right?
Yeah. So basically, there are many things that can maybe have dynamic disorders that are basically, it can be phonons, and that is temperature driven typically. I mean, you go to more disordered phase. And also with pressure, you're changing the phonon spectra, you get soft phonons. So you get two cases that basically another structure is more favorable. But you can also have 0 point effects. So the 0 point motion, if it's enhanced under pressure, and that is also something that is dependent on the structure, you can get they create this disordered phases. I think the other things is like these electronic distortions, like Pyrrole-like or Young-Teller effects, that they are causing motion to remove the degeneracy. So that's another way to look at there are many different reasons for the disorder to be created under pressure. By no means I said that you're detecting disorder through fermiology. What I tried to say was that we are looking at the electronic effects, how the Fermi surface changes under pressure.
Yeah.
Okay, thanks.
Yeah.
Any more questions?
Yeah, I have one, actually. This is Brent Foltz. If we can't calculate it, we can't understand it or something. I'm wondering if there's what the state is of calculating the ground states here of, say, the different phases of lithium, including the 0 point. Have you found any useful calculations or approaches in the literature to do this quantitatively?
So what we did, the molecular dynamics, we can't do the quantum effects. So that is not something that people do. To my understanding is that 0 point effects are being put by hand. So basically added as an energy term rather than being like basically included explicitly. Like, I don't think that, I think I've seen one work on the quantum Monte Carlo studies on lithium, but these are very small systems. I'm not a theorist, so I'm really going beyond what I'm supposed to say, but I don't see that they can do these very complex structures at very, very high pressures. They have looked at it. As for the molecular dynamics, we don't take into account explicitly the quantum effects. So that's...
Yeah, the accelerations are classical usually. There's a couple of tricks, but sometimes they're almost putting it in by hand, as you say.
Yeah, that's my understanding, is that we're putting it by hand. And when I say to, so.
Let me add that there are some codes that have been developed, some approaches that have been developed, and it's quite important for the hydrides, for example, where the quantum effects are large. And these approaches attempt to do it self-consistently. So it's like a self-consistent phonon calculation, but with the quantum 0 point. And it's working fairly well for some systems. Nice papers out of the group in Spain using this method.
Yeah, I think we're on the edge of doing it, yeah.
But it's very important. I think these are extremely, extremely important, and to take into account when we are looking at these very, hydrogen, lithium, stuff that are super light.
Yeah.
Thank you.
Okay. Any more questions? If not, let's thank Shanti for a beautiful talk. And next week, the talk will be jointly sponsored by CDAC and the Center for Matter at Extreme Conditions at University of California, San Diego, a partner SSAA NNSA Center. And I've also reached out to a number of you to give talks. We have openings starting next month, so just contact me if you have, if you would like to give a talk in this webinar series. So thanks very much, and great talk again, Shanti.
Thank you.
Yes, thank you.
Yeah, thanks, Shanti.
Thank you, Rolf. Bye.
Nice talk, Shanti. Thanks.
Thanks, Jim.
Thank you.
Thanks.